Okay, so chapter 6. Chapter 6 is about Introduction to Convection. So, in this chapter, we'll be briefly looking at what are the different types of convections and what are the different scenarios in which you see convection and how you can solve them. And we'll also briefly look at different dimensionless numbers or dimensionless groups. So let's introduce convection again. I know we've briefly talked about convection in chapter 1, but let's see what this chapter has to offer. So convection is the transport of energy due to bulk motion, which is called advection, with molecular diffusion, which is conduction. So whenever we say that there is heat transfer due to convection through a medium, say a surface is convecting through air, that means that it includes energy transport due to the movement of air, as well as it includes conduction through air. So remember, convection includes advection and conduction. Convection can be broadly categorized into two parts. One is forced convection and the other is free convection, or it's also called as natural convection. So forced convection has, again, actually both type of convections can be categorized as internal and external. Now, what do you mean by internal convection and external convection? Internal means when you have convection happening in an enclosed surface, like you have a fluid flowing through a pipe and it's transferring heat, and heat is being transferred from the fluid to the pipe. So this is something that's happening inside an enclosure. So it's called internal convection. And let's say you have a surface, a hot tabletop, which is transferring heat through to the surrounding here air through convection. So you don't have any boundaries. In that scenario, you just have the hot surface and the air. So in that scenario, your convection will be an external type of convection. So you can have internal and external convection in for forced convection and natural convection. Uh, we'll be looking at internal convection and external convection in chapter 7 and 8, and free and natural convection in chapter 9. And let's define what we mean by forced convection and free convection. Okay, so for a forced convection, it's usually driven by an external force or an agent, and usually there is a pressure gradient. So, for example, if you have a fan or a pump that's creating that gradient, or that is imparting some amount of force on the fluid, that will create the fluid to move, and it will generate and it will transfer heat through convection. Now, atmospheric winds can be considered under forced convection because you may have strong winds due to pressure differences or pressure drops, and sometimes you get tornadoes or something like that. So your atmospheric winds can be considered as forced convections if you have really strong winds. The circulation of blood in your body is an example of forced convection because your heart is the external force that pumps the fluid through your body. And typically, for whenever you have forced convection, your convective heat transfer coefficient ranges between 25 to 250 for gases, and it ranges between 100 and 20,000 for liquids. So you see that for liquids, the convective heat transfer coefficient is almost an order of magnitude higher. So for liquids, you'll have more amount of heat being transferred compared to gas for forced convection. But for natural convection, you usually have uh, it's usually driven by a density difference. So what that means is that, as we know that hot air is lighter than cold air. So uh, and why is that so? Because hot air is less, the density of hot air is lower than the density of cool air. So there is a density difference which allows the hot air to rise, and that's the density difference that creates a current, which creates natural convection. Okay, so sea breeze is a good example of natural convection, where say you are on a coast, and let's say you're on a beach, and this is land and this is sea. So during the daytime, your land will be hot, your sea will be cold. It will be cooler than the sand or the land, and there will be a convective current that will be formed and it will generate a cool breeze in that scenario. And for the heat transfer coefficients, you see that for gases, it's between 2 to 225, and for liquids, it's between 50 and 1000. So the difference between uh, forced convection and natural convection is again about an order of magnitude. So basically, if you have forced convection compared to natural convection, your rate of heat transfer will be much higher. It will mostly be higher by an order of magnitude. Okay, so that's the categories of convection and a few definitions and examples of what we mean by forced and natural convection. So everyone here has taken the fluid mechanics course, and we know that whenever a fluid interacts with a solid, it creates a boundary layer. Now in fluids, we call that boundary layer as it's caused due to viscosity of the fluid. So we call it as a viscous boundary layer or a hydrodynamic boundary layer. And let's see what how it looks like. So let's say we have a plate, flat plate, and we have our y direction and x direction, and there's a stream of air or some liquid or fluid, I should say, blowing at a velocity of u infinity. It's a constant flow. That means there's no gradient in the velocity. So it will create an imaginary boundary layer. So the boundary layer that we talk about is just a mathematical expression. There isn't a layer which is formed. It's just a mathematical expression that we use to define where in what regions the viscous effects are dominant, and after what point the viscous effects get less dominant or can be ignored. So this boundary layer here tells us distinguishes those two regions mathematically. So let's look at, and it's usually denoted by rows of x, where x is the distance from the tip of the plate, and rho being the thickness of the boundary layer at that particular x. So at a particular x, we see that the velocity at the uh, at the surface of the plate will always be zero because of the no slip boundary condition, and it will gradually rise, and uh, across the boundary layer it will be the velocity will be same as the free stream velocity, which is u infinity. So just outside the boundary layer, your velocity will be u infinity, but and at this location it will be zero. And as you move away from the surface, your velocity will gradually increase, and that's how your velocity profile will look like. Now, why do we have this? And we have this scenario, or we have this particular profile because of the no slip boundary condition, which is at y equals to 0, which is the surface of the plate. Your velocity is 0, and at your u equals to, at y equals to delta, which is at the boundary, your u is 99% of the free stream velocity. So this 0.99 times u infinity, this may change from textbook to textbook. It might be 0.98 in some or 0.99 in some, but it's usually considered as 0.99 or 994 For our textbook, the definition is 0.99 times U infinity, so we'll stick to that. So after this, we say that after you go beyond the delta x, the viscous effects won't be seen, or you won't have any shears shearing between the layers of fluid. So that's why you don't have velocity changing as you go higher in the y direction. So we define the shear stress as our mu, which is the dynamic viscosity, times the gradient of velocity in y direction. Now remember that u here stands for velocity in x direction. So let me write this down. So u is velocity in x direction and v is velocity in y direction. So uh, in this equation here, our shear stress is equals to dynamic viscosity times the variation of x velocity with respect to y. So your x velocity u is changing as you move up or as you move away from the surface. That's what this says. And for shear stress, we'll calculate this value at y is equal to 0. That means at the surface. So similar to the boundary layer concept in fluid mechanics, we also have a boundary layer in heat transfer, and it's called a thermal boundary layer, and it's caused due to a temperature difference. So let's say we have a plate which is at a temperature Ts, and it's a hot plate, so your Ts is greater than T infinity. Now your free stream is still at U infinity, but it will have a temperature of T infinity. There will be a boundary layer formed due to the temperature difference or due to the temperature gradients. This boundary layer, we'll call it as a rows of T, and it's different from rows of X. So for each problem, your hydrodynamic boundary layer and your thermal boundary layer will be different. They'll be defined by different characteristics. So uh, for if we have a hot surface and flow moving over it, our flow outside will have temperature T infinity, and because we have a hot plate, as we move towards the surface, let me just make it properly. So as we move towards the surface, uh, our temperature will be almost equal to the surface temperature. So this is how our temperature distribution will look like. So in case of the viscous boundary layer, our temperature at y equals to 0 or at surface was 0, but in this case our velocity was 0, but in thermal boundary layer our velocity at y is equal to 0 is the surface temperature. So the properties of the fluid within the boundary layer are dependent on the temperature. So the temperature here is varying, it's changing. So the properties here will change. So your diffusivity or your heat transfer coefficient or your thermal expansion coefficients will be different because they are dependent on temperature. So because your temperature is changing as you move away from the y direction, your properties will change as well. So if you're asked, so your say your volumetric thermal expansion coefficient will be a function of time, temperature, and it will change as you move away from the surface. So to find these values, so if you're asked to find these thermal properties, you need a characteristic temperature at which you can go to the tables or the appendix and look up for these values. So in this scenario, we calculate the film temperature, and the film temperature is nothing but it's defined as an average temperature within this boundary. And I don't know what's going on. So just ignore this. So the film temperature is nothing but the surface temperature plus the free stream temperature divided by 2. So it's the average of the surface and the free stream temperature. So whenever you are asked to calculate thermal properties, and if you have convection, you must always calculate the properties at a film temperature, and the formula of calculating the film temperature is right here, unless the problem states otherwise. Okay, so this is an important formula here, which you should remember what film temperature is and when you use it. So for flow conditions, we determine the type of boundary layer by Reynolds number. So what does that mean? So we define a Reynolds number using a characteristic length, the velocity, and the properties of the fluid to determine if the boundary layer or the flow within the boundary layer is laminar or turbulent, or it's something in between laminar and turbulent. But what do we do for a thermal boundary layer? We need to, we do have a characteristic, we do have with dimensionless numbers. We have different dimensions numbers which we will be looking at, which define which help us determine the type of boundary layer or the type of thermal boundary layer. So what defines the thermal boundary layer? We will be looking at a few dimensionless groups in this chapter and in the next few chapters as well. So moving on to the dimensionless groups, I have divided the dimensionless groups or dimensionless numbers into two. So on the left, we have defined all the dimensionless numbers we looked at in fluid mechanics. And on the right, we have the dimensionless numbers that you will come across in heat transfer, or which are thermal related. So I'll also try to explain what's the analogy between them. So for fluid mechanics, we know that we have Reynolds number, and it's defined as UL by nu. Okay, and it's nothing but the ratio of inertia forces to viscous forces. So your numerator defines inertia forces, denominator defines viscous forces. Similarly, in heat transfer, we define something called as a Grashoff's number, and the Grashoff's number is the ratio of the buoyancy forces. So instead of inertial forces, we have the buoyancy forces, and buoyancy is nothing but force created due to density difference, and the density difference in this case is created due to a temperature difference. So that's why you see a temperature difference term in the numerator, which creates buoyancy. So it's the ratio of buoyancy forces to viscous forces. So you have the viscosity in the denominator. So it is somewhat analogous to Reynolds number. The second is coefficient of friction, which is proportional to the shear stress divided by the dynamic pressure, and it's the dimensionless shear stress, surface shear stress. So similarly, in heat transfer, we have something called as a Nusselt number. So a Nusselt number, the definition for a Nusselt number is HL by Kf, where H is the thermal conductivity of the fluid, sorry, heat transfer coefficient of the fluid. L is the characteristic length, so it might be the length of a pipe or length of a plate, or uh, whatever characteristic length is given, divided by Kf. Now Kf here is the thermal conductivity of the fluid and not the solid. Okay, so H and Kf are the heat transfer coefficients and thermal conductivities of the fluid. So what does this mean? This means that your numerator is the It defines the amount of heat being transferred due to convection, purely due to convection, and your denominator defines how much heat is being transferred due to conduction. So that's what your Nusselt number says, and we'll be looking at these numbers in detail as we move to chapter 6, 7, 8, and 9, and we'll be deriving some of them as well. The next number is sort of a relation, so is the Prandtl number, and the Prandtl number is a relation between fluids and heat transfer. So Prandtl number is defined as the ratio of diffusivities, so ratio of more diffusivity due to momentum and due to and the thermal diffusivity. So for fluid mechanics, you know that the viscosity of the fluid creates or allows the fluid to diffuse or adds a diffusivity term to the fluid. And similarly, your alpha is the diffusivity of a solid or a fluid, and it allows the temperature to diffuse within a particular controlled volume or in a particular body. So Prandtl number here is nothing but the ratio of momentum and thermal diffusivities. Okay, so it is very important that you know the definition of these non-dimensionless or non sorry dimensionless groups. You must know what Reynolds number is, the definition of it, what it means. You must know what Grashoff's number is, Nusselt number is, and Prandtl number is, because we will be using these numbers to calculate either the heat transfer due to convection or to define the type of boundary or type of flow. That means if the flow is laminar or turbulent or in transition. So these are some important dimensionless groups that you must know.